Hi everyone and welcome to this 10th video of BIOB20. In this video we're going to talk about confidence intervals. To have something to work with, we start by creating a Gaussian random sample with n equals 5. And I set the mean to 18.27. You can see that all the values of the sample x are around 18.27. Let's see what happens if I now run a t-test on the sample x. When I specify only one sample in the t-test, the null hypothesis is that the expected value of the sample is 0. R says in the output that this is a one-sample t-test. We can see that the p-value is 2.5 10 to the minus 5. This is a low number, so we reject the null hypothesis. And we are right to reject the null hypothesis, because the expected value of the sample is 18.27. But how can we test another null hypothesis? If I look at the values of x minus 18.27, I can see that those values are much closer to 0. And from what we know of the Gaussian distribution, the expected value of the shifted sample is actually 0. If I run the t-test on the shifted sample, I obtain a p-value which is much higher. The p-value is 0.8, so I accept the null hypothesis. But accepting the null hypothesis that the shifted sample has expected value 0 amounts to accepting the null hypothesis that x has expected value 18.27. So in effect, we're testing whether the expected value of x is 18.27. And we are right to accept this null hypothesis because the expected value of x is indeed 18.27. It's interesting to look at the result of the test for other null hypotheses. If I test a null hypothesis that the expected value of x is 18.25, I obtain a high p-value. It's 0.82. Even higher than previously, so I accept the null hypothesis. It may seem strange to accept two different null hypotheses, but this is important to understand that accepting a null hypothesis just means that we believe that it is consistent with the data. It does not mean that we take it as the truth. In the face of this, it's interesting to see which other values we would accept. We're going to answer this question with a systematic approach using a for loop. First, I create a vector mu that will contain all the values that I want to test. I want to test the values from 15 to 22, and I want to take 1,000 different values. We are going to record the p-values, so I create the vector p-vals that I initialize with 1,000 NAs. I'm ready to create the for loop. I say for I in 1 to 1,000. In the body of the for loop, I write t-test. The sample is x minus mu, the value that we want to test. And I use square bracket I so that I extract the ith value from the vector mu. We just want the result, so we say $p.value, and we store the results in the vector p-vals at position I. When we do this, we can plot the p-values as a function of the null hypothesis that we're testing. We say plot x equals mu, y equals p-vals, and we say type equals L to get a smooth line. We get this funny shape where the p-value around 15 is relatively low. It rises up to a maximum around 18 and then drops again up until the maximum that we tested at 22. For null hypotheses around 18, we have a p-value almost equal to 1, so we of course accept these null hypotheses. For null hypotheses around 15 or 22, we have very low p-values, so we reject such null hypotheses. It would be interesting to see where some usual thresholds of interest are. Let us draw a blue line at 0.05, for instance. We see that all the null hypotheses that go from 15.7 approximately to 20.2 are accepted, at least with the sample x that we generated in the beginning. It's important to understand that this vector x gives rise to a whole range of values a whole range of null hypotheses that are all accepted at threshold 0.05. If I now add a red line at threshold 0.01, I can see that the threshold is of course much lower. Now the range of values that I would accept is wider. In this case, I would accept the null hypothesis that the expected value is 22, for instance. It's normal that this range increases. If I lower the threshold, I am more likely to accept the null hypothesis, so more null hypotheses are accepted in the end. Remember that the accepted null hypotheses are compatible with the data. So in effect, we have a range of values that are compatible with the expected value of the sample X. We know that the mean of the population is probably around 18, and now we have a notion of uncertainty around this estimate. The values in the blue interval correspond to p-vals greater than 0.05, and if I use the function which, I'm going to get their particular position, or their particular index. And if I use min, I'm going to get the index of the first value that is above 0.05, and that's 112. The corresponding value of mu is 15.778. This is the value that we have seen previously on the graph. If instead of the min I ask for the max, I get 760, and the corresponding value of mu is 20.32, which we also saw on the graph. This range of values from 15.78 to 20.32 is quite interesting. They are the null hypotheses that I accept at 5% level. And what's interesting is that these values appeared the very first time that we ran the function t-test. And you can see the values are there in the output of t-test. And R also tells us that this is a 95% confidence interval. So a confidence interval can be viewed as a range of values that are compatible with the data, or a range of hypotheses that I accept at the given threshold. That's what I wanted to share with you. Good luck with the quiz, and see you at the lecture.